The idea of shining light onto metal and releasing electrons is due to Einstein. And it is known as the photoelectric effect. Einstein did so much; it's just mind-boggling. But this experiment, which I think is probably the only experiment he ever did, won him the Nobel Prize. He probably wasn't a very good experimentalist. The early data that is more famous is the one from Millikan, which we'll be using here. So Einstein's great achievement is not that you shine light on metal and electrons come out. It's that he understood what it meant, and it's staring you right in the face in this Millikan data, but it's not that easy to see. So we have h nu equals, oops, not h nu, ek equals h nu minus phi 0. And when h nu equals phi 0, then if hk equals phi 0, then ek equals 0. That means you're just at the point that you're about to release an electron, and that's called h nu 0, the threshold frequency. Below the threshold frequency, here's E equals 0. Here's the E total where it starts off. Here's the light coming in. There's phi 0. At exactly the threshold frequency, h nu 0 equals phi 0. Below the threshold frequency, no electrons come out. No electrons are ejected because you're using an amount of light less. It doesn't make the electron free. Okay. And above that threshold frequency, electrons always come out. So let's write that down. What we see then is if nu is below nu 0, no electrons come out. And the point is, light is a wave. Light has an amplitude. No electrons come out no matter what the amplitude. If, by contrast, nu is greater than nu 0, then we are in this case here. Nu is greater than nu 0. Electrons always come out. And again, light is a wave, no matter what the amplitude of the light. So, for light below nu 0, shining on the metal, no electrons are coming out no matter what the amplitude. If, by contrast, nu is greater than nu 0, electrons are always above, always are coming out, again, no matter what the amplitude. And let's just think about that. And I want you to think of the following image. Let's think of electrons as, here's my electrons. Let's think of them as pebbles on a beach. Pebbles on a beach. And now let's think of a light, a wave with very small frequency. Very small frequency, remember, velocity equals frequency times wavelength, means very big wavelength. And what is the wave that we know that has the biggest wavelength? In the ocean. A huge wavelength wave. Does anyone know one? A very long wavelength, the biggest one is the wave of a tsunami. So a tsunami has a wavelength that's miles long. So a tsunami wave has an enormous amplitude. And I can't seem to get rid of that color. Tsunami has an enormous amplitude, but the wavelength is very, very huge, and therefore its frequency is extremely small. So the tsunami is coming in. Let's say it wants to obey the photoelectric effect. Well, it's below nu-zero because its frequency is extraordinarily small. And therefore, no electrons are ejected, which means no pebbles are moved. That's what this equation is telling you, which sounds like nonsense. And let's imagine something worse. Or I don't know, it's worse, but let's just imagine you go like this in the water. Like make it very, very fast. You wiggle your finger. But very small. You make tiny little waves. So you're going very, very fast. So you go, I can't believe what I did there. You go very, very fast. That means the frequency is extremely high. And that means that the amplitude is essentially zero. But the frequency is going to be above nu-zero. And so I just go little piddly little waves. And according to this equation, should the pebbles be ejected? Yeah, the tiniest little wave, as long as it's high enough frequency, should eject pebbles. Well, none of this makes any sense. And Einstein realized that. And so what did Einstein conclude? Put it in chat. What did Einstein conclude? Einstein concluded light cannot be a wave. That makes no sense. It has a frequency, it has a wavelength, and it's not a wave.